Okay, go.
Chapter 3, Molecules, Compounds, and Chemical Equations. As a summary, recall the law of definite proportions for mixtures and compounds, where we have hydrogen and oxygen, and a water compound. Water molecules have a fixed ratio of 2 atoms of hydrogen to 1 of oxygen. Chemical bonds form attractive forces, and compounds are composed of chemical bonds, namely the Ionic bond, which involves the transfer of electrons from a metal atom to a non-metal atom. The metal atom transfers an electron and becomes a cation, while the non-metal becomes an anion as it receives the electron from the metal. The second type of attractive force, and here's more examples of ionic bonds, specifically table salt, which consists of the metal, sodium, and the chloride ion to form sodium chloride table salt. Metal interacts with a non-metal, and the metal atom becomes the cation, and here's sodium with 11 electrons. It loses 1 electron and becomes sodium plus, while chloride accepts the electron, a non-metal atom, and becomes the negatively charged anion. So, to sum it all, ionic bonds have oppositely charged ions bound by electrostatic forces. And in the example of sodium chloride, a solid phase or a lattice of alternating sodium and chloride anions. And if we look at sodium metal on the atomic scale, you see a nice array of sodium metal. It has a metallic luster, silver gray. As it forms sodium chloride or table salt, you have sodium and purple, and the chloride ion, which is the green, formed when you react sodium and chlorine in the gaseous states. So the other type of bond is a covalent bond, which involves the sharing of electrons between 2 non-metals. And we tend to call them molecular compounds. And here we have phosphorus forming phosphorus chloride. So how do we represent compounds? Well, we represent them using chemical formulas, where it gives us a ratio of the number of atoms or ions present. So for example, water has 2 hydrogen, and 1 oxygen. Carbon dioxide has 1 carbon and 2 oxygen. Carbon tetrachloride is represented as CCl4, where it has 1 carbon and 4 chloride atoms. Types of chemical formulas can involve the empirical formula, which gives you the number of atoms that each element in a compound has, and the molecular formula, which gives the actual number of atoms. So if we have C4H8, propane, the empirical formula for propane would be CH2, and if you have borane B2H6, the empirical formula would be BH3, and for carbon tetrachloride, the only common factor is 1, so both the empirical and molecular formula are identical. Then the other type of chemical formula that chemists tend to use is what's referred to as structural formula. using lines to represent covalent bonds. So in the structure for hydrogen peroxide, H2O2, we can see the structure shown below. Now we've made molecular models earlier, last week, using the ball and stick. So not only can we make ball and stick, but we can also have space-filling models. So methane, CH4, can be represented from the structural formula of C with covalently sharing 4 hydrogen atoms, the ball and stick model, and the space-filling model. On the atomic level, therefore, we need to be able to differentiate between atomic or a molecular compound. Atomic elements exist in nature with single atoms. So for example, we have sodium, neon, carbon, potassium, magnesium, and so forth. Molecular elements do not normally exist in nature, but some of the gases that we're quite familiar with, for example, hydrogen, nitrogen, oxygen, exist as diatomic gases. So are phosphorus P4 and sulfur as S8 polyatomic elements. And so here are the elements that exist as diatomic gases in yellow, and in light pink, elements that exist as polyatomic molecules. So do take a note of that. Molecular compounds are composed of 2 covalently bonded nonmetals. So make sure you have it dialed in that molecular compounds are nonmetals whose molecules compose the constituent atoms. Carbon dioxide or dry ice has 1 carbon, 2 oxygen. Propane, or the gas used in the grill, C3H8. And while ionic compounds have cations like sodium or potassium or calcium or magnesium, they are bound together by electrostatic forces and referred to as ionic bonds. So their basic unit is referred to as the formula units, which is a collection of electrically neutral ions. The ionic table salt, therefore, has a formula unit of NaCl composed of sodium plus and Cl minus ions on a 1-to-1 ratio. So a molecular compound, just like propane gas or water, or carbon tetrachloride, and an ionic compound are table salt. Polyatomic compounds can have charged species that could have more than 2. You would have nitrogen and 3 oxygen molecules, so we refer to that as nitrate, and the ionic charged species would be referred to as sodium nitrate. So therefore, summarizing formulas and names, ionic compounds always contain positive and negative ions. And a chemical formula is a sum of the positive and negative ions. Our empirical formula is the smallest whole number ratio of ions. So we can predict formulas and names by looking at the charges. And we have been talking about representative elements that only form one type of charge, but there are also transition metals that tend to form multiple charges, just like iron, cobalt, nickel, copper, and we'll cover them shortly. So how do we go about naming ionic compounds? So if we have NABR, we would say the metal name, sodium, and then Br, instead of saying bromine, then we change it to IDE. And then if we have Al2CO3, we say aluminum carbonate. If we have FeCl3, we say iron 3 chloride. If we have MgSO4, we say magnesium sulfate. And naming ionic compounds with some examples of the metals that tend to form just one type of charge. Then there are type 2 ionic compounds such as FeSO4, designated as a cation Fe2+, or Fe3+ in Fe2SO43, or copper as a +1, or a copper as a +2. So when we name, we say binary ionic compounds, so 2 binary, there are only 2 elements. So you have the metal and the base, which should end up with an IDE. And when we have KCl, so therefore we say potassium, and then we have chlorine, so then it changes to potassium chloride. So monatomic anions, such as fluoride, chloride, bromide, iodide, will end up being called, if it's F-, will be fluoride, Cl-, chloride, Br-, bromide. How about naming type 2 binary ionic compounds? If we have Fe2+ and 3+, we want to distinguish them by saying iron 2 in Roman numerals or iron 3 in Roman numerals. So in other words, we name the cation, which is the metal, then put in parentheses the Roman numeral, and then name the anion base with an IDE. So if we have CrBr3, we refer to that as chromium. And we look at chromium, we'll have, since it's Br3, so therefore it'll be chromium 3 bromide. And as we go down to the different types of cations, you will note that chromium can have a charge of 2+ or a charge of 3+, hence we say chromium 2 and chromium 3. So how do we go about naming these compounds that have polyatomic ions? So if we have sodium, and we say, if we have NaNO2, we know that NO3 is nitrate, and so it's one less, so we say nitrite, so therefore the compound would be called sodium nitrite. So familiarize yourselves with the different types of names and the formulas. And the more common one, the acetate, carbonate, and really important, hydrogen carbonate or bicarbonate. The hydroxide, nitrate and nitrite. So what are oxygen ions? They are polyatomic ions containing more than one oxygen. As an example, we have NO3- nitrate, and NO2- is nitrite, where SO4-2- is sulfate, and SO3-2- is sulfite. So the smaller number, so 8 goes to ite. And if there are 2 or more, then the prefix, so you want to say ClO-, so hypo, chlorite, or chlorite, or chlorate. And in the lab, we just did the hydrates, our ionic compounds containing a specific number of water molecules mechanically bounded to each formula unit. So if we have MgSO4.7H2O, and more commonly referred to as Epsom salts, we refer to it as magnesium sulfate heptahydrate. So magnesium sulfate heptahydrate. Or if we have COCl2.6H2O, we have cobalt-2 chloride hexahydrate. So once again, remember the prefixes we learned in chapter 1. Mono for single, di for 2, tri for 3, and all the way down to octa for 8. the formula for a compound cannot readily be determined, and so we generally write down. So for example, if we have an element such as, did I go too fast? From its constituent elements, because the combination may have different formulas. As an example, we have NO, NO2, nitrogen oxide, nitrogen dioxide, and N2O, dinitrogen oxide, all the way to N2O5. And so it could have 2 or more metals. And we generally write the name of the element with the smallest group number first. And then add prefixes. So if we just run across acids with, say, HCl, it's H plus and Cl minus, and so we say hydrochloric acid, and acids normally have a sour taste. They dissolve in many metals, and the formula that we want to familiarize ourselves with are HCl, hydrochloric acid, the acid in our gut, and H2SO4, sulfuric acid, the battery acid that we find in our cars. So acids tend to have the hydrogen as its first element, and they do dissolve many metals and give off hydrogen gas. So for binary acids, we will want to write down a hydro for the prefix and end with an ic and an acid, so we say hydrochloric acid or sulfuric acid. And so how do we name H2S? We say hydrosulfuric acid. How do we name HClO3? We call it chloric acid, and we call C2H3O2 as acidic acid. So we've probably heard a lot about acid rain and certain pollutants such as NO, NO2, SO2, SO3. They form acids when they're mixed with water vapor in the clouds, and as they come down as acid rain, and which could flow into our lakes and rivers. And here's a nice nomenclature flow chart as a summary of how we go about naming ionic and covalent compounds. Another important key concept is our formula mass, which is the mass of an individual molecule or formula unit. When we say formula mass, for water, we want to use, as water has 2 hydrogen molecules, so we write down 2 times the atomic mass unit of hydrogen, which is 1.01, and then add that to the atomic mass unit of oxygen, which is 16, to give us 18.02 atomic mass units. So the molar mass of a compound is the mass in grams of 1 mole of its molecules, which is 6.02 times 10 to the 23rd. So we'll be calculating and doing a lot more of this formula mass, molar mass calculations shortly. In the lecture 3, I don't know if you noticed, as we were so busy writing on the board and focusing on the screen, we forgot to turn on the we're kind of retaping the chapter just to see what is highlighted. So feel free to Michelle, and